Here we are again. Welcome to Chapter 6, Chemical Reactivity and Mechanisms. This is a huge step for us. Welcome to really what organic chemistry is about, looking at reactions. And I know it's seemed like such a long time in this class already, but this truly is now getting into what organic chemistry is. We've had a lot of concepts between chapter 1 and through chapter 5. Um, see how far we've come with understanding the molecules themselves. And we've done a lot of background research and diving into these concepts. And the reason for that is truly because we need to understand what a molecule looks like in order to see holistically a reaction and a mechanism. And we're going to be able to talk about reactivity, which is a little bit of a review today with some of our thermodynamics and kinetics from general chemistry. But then we're going to dive right into understanding what needs to happen in an organic reaction mechanism. Now, enthalpy, we should briefly remember from general chemistry. Whether that was the first semester or the second semester, we've talked before about delta H. Enthalpy is the heat exchanged between in the reaction and its surroundings, between a system and its surroundings. Specifically, what we are going to be using delta H for. You might have done it in calorimetry. You might have talked about it with Hess's law. What we are going to be able to use is the idea of delta H as it relates to bonds breaking and bonds formed. So you might have seen this equation before where you have the delta H and it says the bonds broken minus the bonds forms. These are looking at bond dissociation energies. And what a bond dissociation energy is the amount of energy required to break a bond. Remember that bonds are formed because of attraction between a electron and the nuclei. And in order for us to break a bond, we actually have to put energy in to the bond. We have to pull it apart. And in order to do that, it requires energy. So these are all the required energies to break a bond. Why we have that subtraction right here is because we can use the bond dissociation energies, just the opposite sign, in order to say that's how much energy is released to form a bond. When we form a bond, energy is released, and it's the same amount of energy that's required to break it, just the opposite sign. Bond dissociation energies are always endothermic. And so in order to form a bond, we would see an exothermic reaction, just the flip of the sign, right? The other reason why we want to think about this is we do know that when we take two atomic orbitals, let's just say these are 1s orbitals for hydrogen. When we take those orbitals, one hydrogen and one hydrogen, when those two atomic orbitals come together, they lower their energy to form a bonding MO. Definitely lower in energy. There is the higher in energy sigma star that it remains empty, which is why H2 is a favorable diatomic molecule. The electrons must overcome and absorb energy in order to separate these two electrons. So these two electrons right here in the bonding molecular orbital, that's what we're talking about. The energy required to separate those two, remember, would have to go backwards. Higher energy, this is an energy diagram where energy is increasing on the y-axis. And so in order to actually separate those two electrons, you're putting them back into their atomic orbitals, and that is the amount of kinetic energy required to overcome the stability of that bond. Bonds can break in two different ways. The first one that we can see most often is called a heterolytic bond breakage. So bonds break heterolytically, where if we had bond X, Y, where we form a double-headed arrow, and the bond becomes a lone pair. So two electrons moving at once, and the bond will become a lone pair on one specific element of that bond, or one specific atom. What this makes is ions. We saw a heterolytic bond cleavage in acid-base reactions. And so with these ions that are forming, we are breaking the bond with two electrons moving at a time. This is the most often one that we see in this semester, but there is going to be another way that we can break bonds, and we'll briefly see it in this semester, but we'll talk about it even more next semester, and that's called homolytic bond cleavage. With a homolytic bond cleavage, when a bond breaks homolytically, what we start to see is that one electron is going to move at a time. Notice that that arrow looks different. This is called a fish hook arrow, single-headed or fish hook arrow. And the reason why those are different is because there's one electron moving at a time. And so what we get out of these is not ions, but a separation of the bond evenly, and we get what we call radicals. Now, radicals are neutral atoms, but they do not have an octet. And so when we see these arrows, one electron is moving at a time. So we see twice as many arrows, right? We see two arrows for that bond homolytically cleaving, homolytically breaking. Bond dissociation energy is corresponding technically to the amount of energy required to homolytically break the bond, but we can utilize it in heterolytic reactions as well. Here are the bond dissociation energies of some common bonds, which you'll notice is the bond is highlighted red, and that is signifying the specific bond that's breaking. Now, the atom-to-atom bond can change its bond dissociation energy based off of what else is attached to it. Specifically, if we look at something like these bonds over here, hydrogen to carbon, 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 carbon. But depending on what else is attached to that carbon, the bond dissociation energies change. The lower the bond dissociation energy corresponds with an easier to break bond, which we're going to call a more reactive bond a lot. Oops. Let's fit that all in there. So it's good to know what these numbers actually mean. Remember, more reactive means that it actually wants to go make products, right? Something's going to break. And these bond dissociation energies, the higher the bond dissociation energy, it means it's hard to break. It's a stable bond. Lower bond dissociation energies, it costs less to break, so it's easier to break, and therefore it's more reactive. but it is very dependent. Now, these numbers you do not have to memorize. We will try to use both units just to get comfortable with it, kilojoules per mole versus kcals per mole. Essentially, it's just a unit conversion. So both of these you should know how to use, and both of them can be utilized in the delta H calculation of bonds broken minus bonds formed. So we can utilize these to estimate what the delta H is for a reaction by noting in an overall reaction, reactants and products, what bonds are breaking, what bonds are forming, and then do the subtraction. Most reactions involve multiple bonds breaking and forming, and so we'll be able to see a lot of different types of bonds, and we'll do some Lewis structures, we'll do some perspective formulas and things like that so that we can actually see what's breaking and what's forming, and we'll be able to analyze all of those overall reactions to see what actually is happening. Just as a reminder, if the delta H is negative, that is an exothermic reaction. That means that the energy gained by the bonds formed exceeds the energy needed for the bonds broken. It means basically that the products are more stable than the reactants. The energy of the products is going to be greater in terms of the bond dissociation energy. So again, higher the bond dissociation energy, that means it's harder to break those bonds, which means that the molecules themselves are more stable. If your delta H is positive, that is an endothermic reaction, that means that the products are less stable than the reactants. That doesn't mean that the reaction won't happen, right? Delta H is not the only thing to consider in our life here of thermodynamics, but it is a good first step. And so when we talk about delta H, it's really important to remember exothermic versus endothermic and what that means in terms of product to reactant stability. We probably have seen our reaction coordinate diagrams, reaction progress or reaction coordinate here on the x-axis, energy, sometimes written in our textbook as potential energy. Essentially, that means H, enthalpy. It could also refer to delta G at some times. Right now, we'll just think about enthalpy. One of two things we could see just to get this diagram back into our mind. Reactants here are the start of the reaction coordinate. Products are here at the right-hand side at the end of that line. If the reactants are higher in energy than the products, that means that your delta H is negative, right? Products are more stable. Products are lower in energy. If your reactants end up being lower in energy than the products, this would be delta H is positive, or our endothermic reaction. So just reminding ourselves of that. When we have an exothermic reaction, that was when heat was released to the surroundings. Potential energy is converted to kinetic energy, and that kinetic energy was the temperature change that we feel as the surroundings. The opposite is true for an endothermic reaction. Kinetic energy is needed to be converted to potential energy so that those products can actually form at a higher potential energy or a higher enthalpy. And so that's where the surroundings started to feel cooler, because our kinetic energy around us was being sucked in and absorbed into the system. And so when looking at these energy diagrams, we will often use them throughout the rest of the semester to really explain what's happening throughout our mechanisms. And just remember, the energy diagram does look at the thermodynamics, products and reactants, but it also is good to study kinetics. And so kinetics is on here. If you remember where it was, just hold on to that thought, because we'll get there at the end of a couple of these sections. Now, we will be able to, in class, look at bond association energies and do the broken minus the formed and be able to see if the reaction is exothermic or endothermic. This is one that I understand is a really tricky subject. What is entropy? If at this point you have a question, please ask away. Definitely bring it up in class. It is not an easy subject, and I really want to make sure that you understand that it is tricky to talk about entropy. We won't dive into too much about what the real definition of entropy is, but we will be able to see a few ideas and how it fits into organic chemistry. With entropy, a bad definition is the amount of disorder. I'm not going to write that down. That's not a true definition. It can be describing the molecular disorder or randomness, but what we really want to say is that entropy is the number of vibrational, rotational, and translational states of energy of a compound. And really how it is distributed, how these translational, vibrational, and rotational energies and states, how are they distributed throughout the molecule? So what I really want us to consider here is this idea that we saw entropy a little bit in general chemistry as things in gases. Why do gases expand to spread out over a given area? Why don't they just clump up into one side of a container? But the more space, the more freedom that the molecules have to spread out means more entropy. And so that is favorable, right? What is favorable for us means what should happen. And what is favorable for us is an increase in the system entropy. We related this to a positive delta S, right? If delta S for the system is positive, this is what we called increasing entropy. And that was favorable. If delta S of the system is negative, we said that was decreasing entropy, more structure, less disorder. You can think about that as more order, right? And that was not favorable. So when we're looking at entropy, it is one thing that I definitely want to say, how can we qualitatively look at entropy? And that's the key. It's going to be a qualitative look at entropy. We won't have numbers associated with it. I know we did in general chemistry, or a lot of times we do, like delta S's of formation and delta S's of certain bonds. But what we really want to think about is there are two main factors that will affect delta S of the system. So for our qualitative look, what we want to first think about is when there are more molecules, or we can think about moles, right? More moles or more molecules of product, delta S of the system is positive. What this looks like is if we had one molecule going into two. Molecule AB now becomes A and B. There's one molecule and we're making two molecules. You can look at the coefficients of a balanced equation. I'm pretty sure we did that too in general chemistry. If not, no big deal. We now know. And the second factor that we can look at, this one you probably haven't seen, when a cyclic compound becomes acyclic, the delta S of the system is positive. So think about this molecule becoming this molecule. Now, we do know for a cyclic molecule, there is limited rotation. Think of chair cyclohexane. It does rotate, but not a full 360 degrees like a Newman projection did for a alkane. We do know that pi bonds have a limited rotation, right? So that can also be something like this. But typically what our best two things to look at is the number of molecules, comparing the reactants to the products, and limited rotation to full rotation for reactants and products. All right. There's the two. And we'll continue on. Now, what does this mean? Delta S and delta H are the two factors that go into understanding whether a reaction will happen or not. The overarching idea of that, of whether a reaction will happen or not, is called spontaneity, right? Will a reaction happen by itself? Yes or no, right? If a reaction can happen by itself, that's wonderful, right? Doesn't mean it's going to happen fast. It doesn't mean it's going to happen slow. Remember, this is thermodynamics, state functions, only looking at products and reactants and understanding the energies. So if you remember this idea of how this came to be, recall one of the laws of thermodynamics, that delta S total, delta S of the universe, is always increasing, right? And increases is positive for spontaneous reactions. So this delta S total should be positive in order for a reaction to be spontaneous, right? Remember, this is enthalpy, or this is not, this is entropy right here, delta S total entropy of the universe, sometimes written as delta S of the universe in general chemistry textbooks. So depending on where you're coming from, that might have been what you have seen. Delta S of the surroundings is actually a function of delta H of the system and temperature. This is where it gets a little weird with our derivations. But if we know that delta S of the surroundings is this, by definition, the negative delta H of the system, the enthalpy of the system over temperature, we can plug that in to the delta S total equation, right? And then cleaning things up so that we don't have anything divided by temperature. So we just multiply temperature out. What we see is that it's this idea of delta H of the system minus T delta S of the system. What we're trying to do is relate everything to the system in this derivation. And what we get out of that is delta G, Gibbs free energy. Now a negative value, right? If we go back to our derivation here, negative, right? That negative T delta S total is what is becoming delta G. So a negative value for delta G means that the reaction is spontaneous. A positive value for delta G means that the reaction is non-spontaneous. And so enthalpy is important and entropy is important. So we're looking at the overall idea as being, well, if we can look at entropy and decide, and look at enthalpy and decide, is it favorable or not, then we can understand if the reaction itself is favorable. So a couple of things with our Gibbs free energy idea. Favorable, you might have seen something like this chart. If enthalpy is negative and entropy is positive, this always is spontaneous, no matter what temperature. Right? If we plug in any values of delta H that are negative and any values for entropy that are positive, no matter what the temperature is, we'll have a spontaneous reaction. Always unfavorable is where we have an endothermic and decreasing entropy. This was always non-spontaneous. We'll talk about the other ones in class if we have a temperature dependent reaction. Excuse me. But I'll just branch it out right here. If enthalpy is favorable, but entropy is not, we want the smallest temperature possible. Why we want the smallest temperature for spontaneity is because that unfavorable entropy is tied to temperature, right? So we want to try to make that unfavorable aspect as low as possible. If enthalpy is positive, which is unfavorable, and entropy, delta S, is positive, which is favorable, we try to boost that favorable entropy. So high temperatures, we would be spontaneous. We'll play with these a little bit in class, but again, calculations are not super important for us. Just understanding the concepts and being able to relate those concepts to a specific reaction are extremely important for us. Now, just to relate a little bit more about delta G and some of the lingo we used, if delta G is negative, that is called spontaneous. It's also called exergonic. For a free energy diagram, it looks almost the exact same as our reaction coordinate from before, reaction progress or reaction coordinate. On the X, and free energy or G on the Y looks the exact same. Again, reactants to products. In thermodynamics, we look at the difference between the two. There is delta G that is negative. Purple. If our product free energy is higher than the reactants, that was a delta G that is positive. Delta G that is positive is non-spontaneous. Doesn't mean it can't happen, it just needs help. It won't happen on its own. This was called endergonic. Excellent. Equilibrium. This is something that we did a lot of math on before in our life. we're not going to do a lot of math. What we just want to be able to do is understand a couple of concepts here and see how they relate to our reactions today. So again, here's an exergonic process with delta G. It means that the products are favored and they will form spontaneously. But what it doesn't mean is that you'll get 100% product. That's not at all what this means. A spontaneous process means that there will just be more products than reactants at the end of the day. The greater the magnitude of delta G means the greater the equilibrium concentrations of the products. And the same thing goes for an endergonic process, but we're going to stick with exergonic for the time. So why doesn't an exergonic process react 100%? Well, consider this reaction right here, where we're trying to find the minimum value of G, right? The most negative, essentially. And so as A and B start to decrease, right, in concentration, what we're really trying to say is that there will be less collisions of A and B. As you get less A and B, there's not as many colliding with each other. And as C and D start to increase as we switch over to C and D concentrations, there will be more collisions with C and D. Don't forget that to make a reaction go, you need the molecules to actually slam into each other. So as you make more and more products, it's kind of a double-edged sword. Yes, you're making more and more products, but then they can slam into each other and go backwards and make reactants. So eventually the forward reaction rate will equal the reverse reaction rate. And what you get is this minimum value of G. And this is what we call equilibrium. What we've defined for equilibrium is an equilibrium constant, right? Products divided by reactants. And that is what we can use to show the degree to which a reaction favors the products or the reactants. If the KEQ is greater than 1, products are favored. If the reaction KEQ is less than 1, the reactants are favored. And then if the KEQ is equal to 1, neither are favored. Reactants and products are equal in concentration. So KEQ, delta G, delta H, and delta S are all thermodynamic terms. It only describes the relative stability of the products and the reactants, but not how fast or how slow they go, right? And we can use KEQ to find delta G as well. The negative RT, R being the gas law constant, different units, temperature being in Kelvin, and the ln, the natural log of KEQ, will give us the actual delta G. What this actually means is here are some sample values just to understand why things aren't always 100% yield at the end of the day. Even if you do the experiment perfectly, correctly, every single time, you're a brilliant organic chemist, I know it. But it doesn't mean that the molecules are actually going to produce 100% product. So even with a delta G of -6, that's negative, that's spontaneous. That KEQ corresponds to about 10 to the 1, so 10 times as many reactants over products. That's 90% yield, right? So don't think about this as, oh, if it's spontaneous, I'm going to make 100%, right? Even endergonic reactions make a little bit of product, right? And what's beautiful about this idea is that we can actually utilize endergonic reactions followed by a really good exergonic reaction to drive a reaction forward. That's what we're going to start looking at in a reaction mechanism, a process in which reactants become products. How many steps does it take? What do the intermediates look like? You might have heard that word before. We're going to really dive into them now. But remember, thermodynamics is what we've been talking about, right? if we see a reaction coordinate with the reaction progress on the x-axis and some sort of energy on the y, right? When we start putting in the lines, right, all we know is reactants and products. Here is thermodynamics, right? Kinetics is what you get in the middle. This is kinetics. And it's together with thermodynamics and kinetics that we can truly understand everything that is happening in a reaction. So just because a delta G is negative doesn't mean that the reaction is going to happen fast or slow. All that means is if delta G is negative, it's going to happen on its own. It's spontaneous. So it could be something like a combustion reaction, which is very, very fast, very exothermic, very, very exergonic, happens very fast. Or it could be something like diamonds going to graphite. Everybody's diamond ring is going to eventually turn into a pencil. But it takes millions and millions of years for that spontaneous reaction to take place. So what does that mean for us? Thermodynamics is not the only piece of our puzzle. We also need to understand kinetics. And so the rate of the reaction, how fast or how slow, how many molecules are colliding at a given time period, are all very important. Now we are going to deal with 5 things that affect the rate of the reaction. We might have seen some of these, but we're going to be able to see a lot more and see a holistic picture once we get into reactions in chapter 7. I know we're not even in reactions yet. This is just still understanding what we need to know for the reactions in order to get the reactions, still learning the language. Now we do know for kinetics, this is when we started talking about rate laws, where the rate of the reaction was equal to K, the rate constant, times the reactant concentrations, or whatever was dependent for the reaction to go forward. The rate determining step told us this rate law. And so this idea that the rate is dependent on the rate constant and the concentration of the starting reactants, we really needed to hone in with the idea of to what degree, right? What changes the rate of our reaction? Concentration of reactants was first. We'll talk a little bit more about activation energy. We'll see how temperature plays a role. We'll see how the actual shape of the molecule and those sterics that we talked about, big, bulky things, tend to move slower. Small, tiny little things can wiggle in and react faster. And what a presence of a catalyst means. We won't talk too much in depth about all of these, but what we will be able to do is quickly be able to identify what reacts faster or slower based off of these 5 concepts. Now, the order of the reaction is represented by the exponents for the reactants in the rate law. If there is one exponent or one molecule, that is what we call a first order reaction, we are going to call that unimolecular. Uni for one, molecular for molecule, right? The second order reaction that we are going to see is when we have 2 reactants that are going to collide together. This is called bimolecular. Your book does go into third order reactions. We're not going to do third order. We'll talk about first order and second order a lot. And that's primarily the ones that we'll see in this semester and in the first year of organic chemistry. And so just ignore third order. It is an omit right now from our textbook. All right, activation energy. We're going to start here. I think we've done a lot with the concentration of the reactants. And so the reason why I just kind of want to not remove it from our discussion, but we know that as the concentration of the reactants increases, the rate increases. That's great. we're going to talk conceptually about the other four. So activation energy, the energy barrier between the reactants and the products. So I'm going to pull up our reaction coordinate diagram again. I know it's been a long time, and I'm just going to have potential energy here. And we'll just slap on some reactants and products. And this is where we can talk about let's make that P look better. Where is the activation energy? It's the difference between the reactants and what we are going to call the transition state. This is a symbol right here. This orange guy is a symbol for the transition state. And the amount of energy separating the reactants and that transition state is what we call the activation energy. So it's the minimum amount of energy required for a molecular collision to result in a reaction. And that energy barrier is required for the collision to be effective. So when two molecules collide in a reaction, two reactants come together and smush. They need to have enough energy to get over this hill in order to make products. So you can think about this purple line as really a pathway of how are the reactants forming products. The higher the activation energy, that corresponds to, so I'm going to try to make this the exact same, that corresponds to a slower reaction. So I want to look at these two potential energies. The purple one will be my first one. Let's do this blue one, and I'll try to get the reactants to be at the same level. Woo! And the products to be at the same level as well. Now, comparing these two, be very, very aware that I'm trying to compare apples to apples here, not apples to kiwis. I'm trying to make the reactants the exact same energy and the products the same energy. So I'm only talking about kinetics. I only want to talk about the middle portion of this reaction coordinate diagram. And if we look at this activation energy, it is much higher. The higher the activation energy corresponds to a slower reaction, because the amount of actual molecules that would have that activation energy, enough energy to get up to that transition state, is probably not as high as one that would have a lower activation energy. Lower the activation energy, faster the reaction. Excellent. All right, temperature. Raising the temperature will result in a faster reaction. Why? At a higher temperature, more molecules have more kinetic energy. And so let's think about, here is the activation energy barrier, right? Energy on this x-axis and number of molecules on the y. When we increase the temperature, what we are doing is we are shifting the kinetic energy available further to the right here on this chart. To increase the amount of kinetic energy, remember, temperature is proportional to kinetic energy, and kinetic energy is directly related to velocity. And so when we think about these molecules moving faster, they're hitting at a higher energy, right? They're colliding faster with a higher velocity. And so therefore, more molecules have enough energy to produce a reaction. There's just more available energy to reach that transition state, to reach the activation energy. And we can see that right here with this extra amount of molecules, right? The area that has been pushed back past to the right of that activation energy results in more molecules with enough energy. So for steric considerations, think about steric hindrance. Think about, I like to try and relate this as much as real life. Steric is important to really understand for all of our reactions. So I'm a mom. Um, I have a child, and he is a handful, right? All kids, demand attention and need help and need food and need happiness. So when I go to the market, um, I try my best to do one trip from the car with all of my groceries, all my food for my child, so that I can get it in the house as quick as possible. In reality, putting all of those bags, because I have a child who eats a ton. He loves food. So pulling up 10 bags from the grocery store at once creates so much weight and bulk around me. I don't move faster, I move slower. That is steric hindrance. If I had one bag, then I could move really fast to the door, go back and forth, back and forth, back and forth. But every time I try to collect all the bags at once. But I still need to remember, when molecules collide, they have to be able to move fast enough, okay, have enough kinetic energy. But if they actually are big and they have a lot of things around them, they might not actually collide in the right way. So thinking about a couple of subcategories here with steric hindrance, the more steric hindrance you have, it will affect your rate of the reaction. Typically, an increase in steric hindrance means a slower reaction rate. But think about the idea that molecules collide, and so the orientation has to be correct. We'll see that a lot in chapter 7. Energy required. So we can think about the kinetic energy and that 1/2 mass velocity squared. If you're not moving fast enough because you're a bigger molecule, then you're not going to have the right uh, amount of energy. And so the steric considerations there are the bigger molecules move slower, and so they don't react as fast. And on the last one that we'll talk about a little bit more when we get into chapter 7 is the conformation of the collision. Mainly looking at ring structures for this last one, we'll see differences in axial and equatorial groups, and so we'll dive into that further. But again, all of these steric considerations are hard until we have molecules and actually have a specific reaction. Sometimes sterics are important, sometimes they are not. So I know steric hindrance is always one that you might have heard other people say. It's always resonance or steric hindrance. So just write that for an exam. That's not always true. That's not a good thing to remember. Steric hindrance happens on specific molecules that require a specific orientation and a specific energy and a specific conformation. The more detailed you get with the actual reaction mechanism, sterics are important. All right, and a catalyst, the only thing that we're going to talk about with a catalyst is that it speeds up the rate of the reaction without being consumed. So a catalyst will be seen at and consumed as a reactant, but it will also be produced as a product. And so it's overall not utilized or not consumed fully in a reaction. It's utilized and then reproduced. It doesn't lower the activation energy of the typical reaction. What it actually does is it provides an alternate path. Notice this diagram right here with the catalyst, the red line, it made a squiggly path. Usually the catalyst will lower the activation energy of this rate determining step. And so that's what this diagram truly shows, is that catalysts such as enzymes are a great example of a catalyst. We do have some organic organometallic molecules that we'll see next semester that are great catalysts as well, if you're thinking of the organic realm versus the biological enzymes. but the catalyst does truly just provide an alternate way for the reaction to occur, and that alternate way is faster for that rate determining step. All right, so again, overall, what did we just learn here? Or what did we just remember? There are a couple things when looking at a reaction coordinate diagram. Reactants to products, that's thermodynamics. The pathway at which those happen, where we get a transition state, where we get an activation energy, that's kinetics. Thermodynamics tells you the stability of the reactants and the products. Kinetics tells you how fast a reaction will go. They are completely different concepts. However, together, they are an extremely powerful tool to understand how long are you going to be in the lab? Is that a good way to mass produce a molecule that's a drug? Is that an option for a biological system to respond? Is whatever we're looking at, thermodynamics and kinetics is a holistic view of understanding a reaction. So we're going to look at these reaction coordinate diagrams a lot in class, but what I would say is let's make sure that we can read them a little bit better. Multiple steps, right? When we see a bunch of squiggly lines, reactants are always at the beginning, products are always at the end. When we start thinking about the kinetics, what happens in between? I'm going to label this as step 1. That first hill is going to be a transition state. I'm going to say transition state 1. It will have an activation energy, EA1. What's important to note is that does not need to result in a product. It results in an intermediate if there's a second step. This is step 2. Transition state 2. Activation energy 2. Right? Between two steps are what we call intermediates. They're molecules that are able to be isolated, right? But they are not the final product. So an intermediate is the species formed during the course of the reaction. They are an energy minima, right? There's a little valley there at the intermediate. And they are observable. They're actual species, and you can exclude them. You can pull them out. You can identify them, but they usually aren't the final product. The transition states are the hilltops in between those for those two steps. The two hilltops, they're maximas, right? They're energy maximas. They're the energy required to get over the hill, to proceed the reaction. Transition states are not isolated molecules. They're the in-betweeny. They're the positions where we can't actually see them in real life when bonds are breaking and bonds are forming. So when we draw a transition state, we'll see that they're going to be not real molecules, just more like theoretical points when the bonds break and form. We'll call this step 3, this final step. It also has an activation energy, right? And it comes from an intermediate and goes to a product. So there are 2 intermediates here, 3 steps or 3 transition states, reactants, and products. What we are going to be able to do is look at a reaction coordinate diagram for specific reactions and be able to identify an intermediate or a product or a transition state. So let me just show you one reaction that we are going to do in this class. And I won't put on any arrows yet, but you can kind of start to see what's happening. Overall, center that. Overall, we have this tert butyl bromide. We have a bromine attached to 4 carbons, right? Bromine's going to leave, and we're going to form ions. And then chlorine ion will be in the reaction. It will come and replace the bromine, and we'll see the chlorine gets attached. Now, for a reaction coordinate diagram, what we want to be able to see here is that there are 2 steps, right? The first step is when the bromine actually gets kicked off, and the second step is when the chlorine bond forms. Overall, carbon to bromine bond breaks, carbon-chlorine bond forms. We can actually go ahead and do the delta H for that, but right now we're just going to look generically and try to make the reaction coordinate diagram here. Now, if we look at these right here, these are the intermediates. They're not the products. They're what's in between the 2 steps. So we can see reactants are going to form intermediates. I like to put a little level there so that we have room to breathe a little bit before we go into step number 2. Now, right now, you don't need to know which reaction is exothermic or endothermic, exergonic or endergonic, but what we should see is 2 transition states, 1 set of intermediates, and we can actually draw the molecules that are there. Nice. And we can start to identify when we get into reactions what that means and putting the molecules in place. Now, when we look at a reaction coordinate diagram or an energy diagram, we should be able to identify some sort of structures. So with the transition state idea, this is based on the assumption that we can generalize the structure of the transition state depending on whether a reaction is exothermic or endothermic. If we have an exothermic reaction, the transition state is closer in energy to the reactants. And so therefore, the transition state, it actually mirrors the state of the reactant. So whatever the shape of the reactants is, technically we can start to think about the behavior of that transition state to be close to the reactants. And the same is true for an endothermic step or process. The transition state is closer in energy to the products, so we should be able to look at the products and identify something about the transition state based off of that. When we get into actual reactions in Chapter 7, this will become a little bit more apparent. But what this means is in an exothermic reaction, reactant stability is very important to understand the transition state stability. In an endothermic process, the products are important for their stability to understand the stability of the transition state. Nucleophiles and electrophiles. This is where we're starting to dive into brand new territory. For a reaction, polar reactions, we are going to see ions as reactants, intermediates, or products, right? Negative charges are attracted to positive charges. Opposites attract, we know that. But we also know that electron-rich species mean that they have a lot of electron density. We want to relate those to negatively charged items, right? It could just be a delta minus or an actual minus. It might be a lone pair. It could be a bunch of different things. But we want to start thinking about, does the atom have a lot of electrons? Or is the atom deficient in electrons? Are they more positively looking? And so when we look at this carbon atom, That's what we're focused on right here, is the carbon in these two molecules. When carbon is bonded to chlorine, carbon is electron deficient because the polar bond between carbon and chlorine is pulling the electron density towards the chlorine. So carbon is feeling electron deficient, looking more positive, not an actual positive charge, but a delta positive. When carbon is bonded to lithium, lithium being a metal, then we start seeing that lithium pushes its electron density towards carbon, making it electron rich, having more electron density closer to the negative charge species, because lithium will take on the delta positive, carbon, more electronegative than lithium, takes on the delta negative. So in a reaction, we have to be able to start to label electron-rich species and electron-deficient species. A nucleophile, nucleus loving from the Greek. Nucleophile means that it is an electron-rich species that is looking for a nucleus to pair with and to love and cherish. So nucleus loving, what's in the nucleus? Protons. Electrons attract to those protons. So a nucleus loving species must have a lot of electrons to donate. That lithium to carbon molecule has carbon being the actual nucleophile. We can think about lone pairs and a negative charge. Oxygen in this ethoxide ion is the nucleus. Even without a lone pair, or without a negative charge, lone pairs are still considered nucleophiles. We will also see pi bonds, the electrons in the double bond or triple bond. Draw a triple bond on here too, just so not discriminating against our pi bonds. Those will also be nucleophiles. Now, the more polarizable the nucleophile, the stronger it is. And so we'll be able to talk about what that means in just a little bit. An electrophile is the electron deficient species, electrophile, so electron loving, something that's looking for electrons, is going to accept a pair of electrons. So these are going to look like more like acids, whereas the nucleophiles look like bases. The electrophiles look like acids. The most, though the easiest one to think about is the carbocation. Remember that carbocation is an empty p orbital, and that's what gives it the formal charge of +1. We can also see polar bonds when they again give carbon a delta plus charge. So there's the electrophile, there's our electrophile. Carbocations and partial positive atoms are electrophiles. Typical ones that we will see, delta negatives, lone pairs, pi bonds, those are all nucleophiles. They're electrons that are ready to go out and attack a nucleus. Electrophiles are our delta pluses or our empty p orbitals, and those are the ones that we are going to focus on. Curved arrow mechanisms. Now, we already kind of did this in acid-base reactions. When a base meets an acid, the base lone pairs will go pick up the hydrogen and kick off a minus so that we make BH, the conjugate acid, and A minus, the conjugate base. Now, with these curved arrows, this is an acid-base reaction, or what we are going to call a proton transfer. But again, it's starting with something that is electron rich, the base, going towards something that is electron deficient, which is the delta plus on the proton. So we already do know one type of ways that polar reactions show curved arrows and mechanisms. It's a proton transfer. We're going to go through all of these. A nucleophilic attack, we're going to see a loss of a leaving group, we'll see proton transfer again, and then we'll talk about rearrangements. And all of these curved arrows or mechanisms are used to show how the electrons move as bonds are breaking and forming. For a nucleophilic attack, a couple of things that we can see. Essentially, what we're going to be looking for is a nucleophile attacking an electrophile. That's the main goal of a nucleophilic attack. Bromine has the electron, so I'll highlight those a little bit bigger. There's my nucleophile, and it's attacking, pointing right to the electrophile. There is one way to do a nucleophilic attack. You could have an ion, right? That's a good way to identify a nucleophile. Doesn't mean it's a great nucleophile, it just means that it is going to be deemed the nucleophile, and arrows usually start there. Another way that we can look at a nucleophilic attack is attacking a pi bond. We'll see this one a lot next semester. Nucleophile, again, got some lone pairs. It can attack an electron deficient center because of a polar bond. Now that carbon is the electrophile, but that carbon already has 4 bonds. So what has to happen is a pi bond can break and roll up onto the oxygen. We'll practice these a lot, so don't worry about them too much right now. It's just being able to identify, can I see what type of bond I have? Or what type of curved arrow am I forming? Excellent. Nucleophilic attack can also be a pi bond. I have one more to show you with this. Again, this will be next semester. But with those aromatic compounds, they're some of my favorite. You might have a nucleophilic attack where the pi bond breaks, attacks a center, and which pi bond do you kick off? Well, you only need to kick off one, and it doesn't matter which one you kick off if you have multiple and they're all going to the same atom. But what's really important to note is that those formal charges, right? So note where the atom is going, how many things are on those atoms, and make sure that the formal charges of the reactants and the products are equal. Excellent. Only one carbon atom from the pi bond uses the pair of electrons. So notice here, carbon number 1, carbon number 2. Only one carbon can collect that new bond. The other one will get a positive charge when a pi bond will react as a nucleophile. There again, there's the nuke. And that sulfur is the electrophile. We'll get to all of these reactions. What's important to just note right now is, again, the process, right? The definition. Loss of a leaving group. We're just going to do a very similar one to what we did before. We could have a bond simply break. That's the loss of a leaving group. Bromine is leaving. The heterolytic bond cleavage of an atom where it takes the electron pair away from whoever it was bonded to. Right? There's our loss of leaving group. Bromine is the leaving group right there. Or bromide is the leaving group. We could also think of a leaving group having more than just that one arrow, but we'll stick to just the one arrow right now. Proton transfers. Proton transfers happen readily between acids and bases. We can look at an acid and base and call it more specifically a nucleophile attacking an electrophile. But when that nucleophile attacks a proton that is an electrophile, that specifically is a proton transfer. So this could look also like a nucleophilic attack. However, the nucleophile is specifically attacking a proton, so it's a proton transfer. Nice. Rearrangements. Carbocations can be stabilized by neighboring groups. The orbital overlap that's happening here with a carbocation is called hyperconjugation, very similar to our staggered formation, why staggered was more stable than eclipsed. So looking at this methyl group, when you have a carbocation, it's an empty p orbital, and it actually can be stabilized by a sigma bond right here. The sigma bond that is filled can start to hyperconjugate and donate some electron density towards the carbocation. That is stabilizing, just like the hyperconjugation was before for our staggered Newman projections. So the more carbon groups you have around a carbocation, the more stable it is. Methyls, where there's no carbon groups, a methyl carbocation is the least stable carbocation. Will not form ever. Don't even try, it's not going to show up. Primaries, sometimes written as primary carbocation by myself, those are not super stable. They're more stable than methyl. Right here is a big dividing line of what we typically see. Secondary carbocations can form. There's enough hyperconjugation with two R groups donating electron density towards the carbocation. Tertiaries are the most stable of our R group systems. Allylic, we've seen these before, resonance stabilized carbocations are the best. So if you have resonance right next to that carbocation, these are even better than tertiary. The increasing substitution increases the stability of the carbocation, and that is just due to the increasing number of adjacent sigma bonds that can align with that empty p orbital and hyperconjugate. So with rearrangements, what we want to be able to look at is there are two types. The first one is called a 1,2 hydride shift, and it will happen when there is a carbocation adjacent to a more substituted carbon and has a hydrogen to move. So here we have a secondary carbocation. It's a carbon with 1, 2 R groups, right? So it's a secondary carbocation. Next door, there's a tertiary carbon, a carbon with 3 R groups. The hydrogen on that tertiary carbon will shift. I'm going to draw in that hydrogen over here just so that we can see it move. And what happens is that hydrogen picks up the electrons as a hydride, H minus, and plops itself down on the neighboring carbon, the carbocation. The reason for that is because when it does that, we create a tertiary carbocation, one that is more stable. The only time this will happen, the only time rearrangements ever happen, is when a carbocation is secondary and can become tertiary, or primary even. We can sometimes see an intra type of a rearrangement. It's going to be super fun. We'll get there. But overarching idea, something is going to become more stable. A carbocation is going to become better. A 1,2 methyl shift can happen as well. Hydrides and methyls can shift. Nothing else can shift because nothing else is small enough. So if you have, again, a secondary carbocation, and say you have a quaternary next door, one that is a carbon with 4 carbon groups, a methyl can shift over. Notice the origin of that arrow is from the bond. That bond can shift over a methyl group. And again, the carbocation becomes more stable. We'll practice these a lot in class. I made this diagram I think it's important to be able to know these heterolytic reaction types. Please don't try to memorize them, but definitely look and find the pattern of them. I think that would be extremely important for us in drawing curved arrows, in making sure that we don't have any issues. The octet rule is important to remember, so we'll be practicing that a lot. And I will see you all in class. Thank you so much.